My name is Richard Williams, and I've been with Staddies now for, I don't know, 7 or 8 years, something like that. But prior to that, I spent 38 years in the chemical industry as a chemical engineer and Six Sigma Master Black Belt. And someplace along the way, I solved a lot of problems. Things that maybe shouldn't have been problems at all. In fact, I presented to the Staddies October 2023 conference. I gave a presentation on a responsive surface design called RSM Safe the Circuit Board. And it was kind of a Herculean effort to solve a rather substantial manufacturing problem. And the more I thought about that, the more I realized that, well, that really shouldn't have been a problem at all. That it was kind of obvious that what became a problem, which was going to be a contaminant sometimes present in a raw material, that really was quite easily, understandable before the product even got launched. And perhaps we should have thought about that and worked on that issue before we launched the product, right? So we didn't prevent that problem. So that was one of my motivations to create this webinar. Actually, this is going to be two webinars. There's a follow-up in October, and I'll talk more about that a little later. It's a big topic, really. And the other reason I'm doing this webinar is honestly, when I do trainings, I get out in the field and I talk to folks like yourselves. The whole concept of robustness comes up quite frequently. I would say probably most commonly if I'm teaching in the pharmaceutical world, I always hear somebody want to talk about robustness. The idea that we want to create products and processes that will function, or that when we release it to manufacturing, that we won't have an onslaught of problems that take place, right? How can we prevent problems from the beginning? The issue is robustness studies can be, well, basically every tool we have in the toolkit can be applied in the world of robustness. So when I'm asked this question, I'm a little bit deer in the headlights because it's such a big topic that I really don't know how to respond. And so what we've done now is we've created this webinar and a follow-up webinar to give a more proper, full explanation. I'll say a fuller explanation for the topic of robustness and what kinds of studies could be swept into that idea, right? So that's where we're going with it. I will assume that you have somewhat of a basic knowledge of DOE at least, that you're familiar with the concepts of factorial and response surface designs. If you don't, I'll give you a couple of pointers along the way. But the idea is we're not going back to the fundamentals of what a factorial design is or what a response surface design is. What we're trying to do now is to showcase how these tools can be used to accomplish this thing called robustness. Okay, but what exactly is robustness? Well, let's just kind of take a real quick example that you might think about where we're designing tires. Okay, we're manufacturing tires, and we put these tires out in the field, and the goal is to have a good stopping distance, amongst other things you could think about. But we want to have a good stopping distance. But in the field, out there in the real world, you have all kinds of different conditions, don't you? You have, ice and snow and loose gravel and highly textured pavement and smooth pavement, right? So you have all kinds of different, what I'll call noise factors that might impact the stopping distance of the tire, right? So the idea of robust design would be to come up with a tire design that is relatively insensitive to all of those different noise factors that you could throw at it, the type of pavement you're on. Okay, so that would be an example of a robustness study. However, it's also important to realize that it's not just for the product itself once it hits the field. We can also think about, you and I create products and processes, laboratory, pilot scale type things. And we may end up with a situation where we're going to release that to manufacturing, and manufacturing might have a hard time controlling the parameters that we say are important, right? So we're going to need to know what kind of flexibility that we're offering them, or maybe they'll encounter noise factors that we hadn't even considered. So that's kind of the domain of robustness studies, and the whole point and purpose to this is we want to prevent problems, before they even start. Okay, by studying them and understanding their impact in advance. So that's a little bit where we're going. Now, to prevent audio disruptions, everyone is muted on the call. Um, you can, if you have questions, there is a question area in the uh, GoToWebinar section. I will take a look at that from time to time as I speak. And the simpler ones, I'll go ahead and answer. The more complicated ones, if there are, I will, if it's going to take too much time, I'll have to follow up with a response to those later. You can subsequently send questions to stathelp at statease.com, or if you want to contact me directly, it will be richard@statease.com. Note that the slides will be recorded, and this webinar will be posted on the webinars page of the StatEase website for your review. I will be going through a lot of content fairly quickly. So I guess what I will suggest to you is, if you capture this at, 50, 60, 70%, that's good. That's probably the expected level. But if you do want to come back and revisit this, like I said, the presentation will be posted again so that you can dig in a little bit more deeply if you have the need or desire. Okay, so here's what we're going to do. The little diagram here shows that we have a process. We have a controllable factors, our X's, the factors that you and I tend to think about when we do a designed experiment, right? We have time, temperature, catalyst, as you'll see in the example we go through. We also have noise factors, things that are out there that are going to try to confuse the story a little bit, right? We're going to have some variation in our ability to set the control factors, but we'll also have some other factors, like in my little example, we're going to see that we have a contaminant that rears up once in a while. What will that do? And the goal is to, of course, have some desirable responses. In my case, it'll be conversion of the reaction process that we're studying. And we want to put this whole study together and hopefully either identify noise factors or, in an ideal world, prove that the noise factors we're studying actually have no impact and we're happy. Okay, so let's dig into what a robustness study looks like. A robust process is minimally affected by sources of variation. Okay, so that can be, like I said, the sources and the variation in our factor settings. Or most commonly, people think of it being, external noise factors. Kind of like the tire example, where you have different kinds of pavement that you're going to be exposed to, right? So they're external to the system itself. But you can have, all kinds of different noise factors. You'll see a handful as we do our example problems. Generally, though, robustness testing can include, the expected variation for both our controlled factors, the X's, and the uncontrolled noise factors. And finally, the ultimate robust study will seek to find the process factor settings that simultaneously maximize our performance and remain insensitive to variation in both X's and the Z's. This is actually going to take us into some more sophisticated designs, and that's really what the October presentation will be about, and I'll tell you more about that at the end of this presentation. So you may have heard the word ruggedness and robustness, or use them interchangeably, or just frankly, we're unaware of what the difference might be. And that's okay. I spent time in that place as well. I wasn't really clear on the difference between ruggedness and robustness evaluations, but we're going to try to clear that up for us right now so we understand what we're trying to do in this webinar. A ruggedness evaluation is typically a very small design. Then what we are trying to do is demonstrate insensitivity to noise factors. Okay, so we come up with our optimal factor set points, if you will, and then we can imagine that, well, there's 3 or 4 or 5 or 10 different things that we want to make sure that when this product goes to the manufacturing floor, that we want to make sure that these things don't cause any problems. And the goal of that experiment is to demonstrate, in fact, that we are insensitive, to those things. That's kind of a ruggedness testing. Now, things get a little bit more complicated if along the way we find that these noise factors, do matter. Okay, so that's going to be something we're going to look at as we continue. Now, as compared to ruggedness, a robustness test seek to understand the influence of noise factors, right? So instead of hoping that we don't find anything, here we imagine that we might, and we want to understand specifically what it is that's causing us problems, so that we can establish controls. Okay, so it's a little bit more of an advanced idea than a ruggedness test. Now, which tool, should we use? Ruggedness, robustness? Well, it kind of depends on what we think we're going to find, and how many factors that we have. If we imagine that the things we're studying could very well have an impact, right? So this is a guessing game to some degree. I mean, if we're quite confident that they won't, maybe we have prior experience, but we just want to demonstrate that we're okay, then maybe the ruggedness test is the way to go. But on the other hand, if we suspect that these things really are going to have an impact, or they might, then we might want to go for a little bit more aggressive design, and that'll take us into what I'll call robustness designs. If I have a whole bunch of factors, and a whole bunch meaning, say, over 8, 9, or 10 things that I'm trying to look at, then maybe all I can afford is a ruggedness test. But that could lead to some issues as we continue down the journey. By adding runs, though, we can make either approach work, but that means what? More work. Okay, so that's now just a little footnote here. This whole ruggedness thing, there's an ASTM standard around that, E1169. My colleague Mark Anderson was heavily involved in the creation of that. So ruggedness are a very useful and real thing. I'm going to try to focus on some other ideas in the world of robustness. Okay, so here's, maybe you're familiar with this chart, maybe you're not, but this is our famous SCO experimentation strategy. So here, what we're looking at is we typically talk about screen for the factors. Maybe I have 10 or 12 things that I think could impact a process, so we screen so that we're only working with a critical few. And then maybe we do some characterization where we understand the interactions between these things. And perhaps we're going to go through and do a complete response surface design to find the optimal set points for the factors that we've identified as being important, right? We've optimized the system. In general, we view robustness studies as being something that's done after that. So we've identified our optimal conditions, and then we're into what we call the confirmation, window down here. And typically our first confirmation might be, well, let's go run a few trials at the optimal conditions, make sure that it works as advertised. But we can also do our robustness test or ruggedness test in this phase as well, where once we find the optimal conditions, we do further work to look at the impact of these noise factors. Okay, so that's kind of where it resides in our overall strategy. We're going to see this slide at the end when I talk about the next webinar as well, so we'll revisit that. So let's get in by doing something. Okay, so we're gonna look at a little chemical case study, and that's probably comes from the fact that I'm a chemical engineer and I see the whole world that way. But anyhow, we're gonna do a chemical case study, and we're gonna look at we're gonna evaluate the process performance against uncontrolled conditions expected in the field once we release this to manufacturing. Okay, so first, what we're going to do is I'm going to go quickly through this part. I'm going to assume you kind of know what we're talking about here. We're going to do just take a look at the output from a central composite response surface design and optimization design. So what I'm saying here is we're going to do this little step real quickly, and that's going to set the stage for the subsequent robustness study that we're going to do. Okay, so here's my factors. I have a chemical reaction I'm dealing with. I have 3 factors: time, temperature, and catalyst. And the goal is to maximize conversion. So it's not a real, it's not rocket science. We're just looking at 3 factors to optimize the conversion. After we do that, we're going to come back and take a look at a robustness study, right? So we find the optimal conditions. And then what I want to find out is, well, when I release this to manufacturing, they may have an imprecise control of the temperature, right? That in the lab, I was able to control it pretty good, but out there in the manufacturing world, their temperature control system, it's going to fluctuate a little bit. So can I tolerate that? There's also a contaminant that's occasionally brought in with a reactant. Is that going to cause us any issues? I have two choices for a vendor. I can use vendor A, which is kind of the base case, or I can have an alternative supplier for the catalyst. Okay, so that's something manufacturing might throw at me. Okay. The reactor type, well, I'm currently using a glass-lined reactor, but if manufacturing wants to someday, if we're successful, they want to expand this process, well, they might want to use the stainless steel reactor that's sitting right next to it to kind of gain some more capacity. Will that give me any trouble? We also have the atmosphere. So in the liquid in the reactor vessel, there's a headspace over the top of it, and I can fill that with nitrogen, or I could just let air be in there, right? Does that cause me any problem, one or the other? Do I have to incur the expense of putting nitrogen there? And also, if temperature matters, maybe I'm going to have some inability to control my cooling time, right? So maybe the cooling time will be long or slow, and we want to evaluate whether or not that's going to have an impact on my conversion as well. Okay, so I got six things that I'd want to evaluate in my robustness study. So we do a central composite design to find the optimal conditions before we do the robustness study. And we look at time, temperature, and catalyst. We do this little study. And here's the inputs for the response surface central composite design that we did. And in the end, here's what we have. Pretty simple stuff. We've created a predictive model to navigate the design space. We have three factors, all of which appear to matter. We have some interactions, and we have some quadratic behavior for B, which is temperature, and C, which is this catalyst. So there's something going on there for us to take a look at. Okay. Note that one of the outputs of the response surface is standard deviation, right? So that's going to focus on how precise we can be in making predictions. That's going to be a value we're going to want to remember. So this 0.76 number is something we're going to want to pay attention to. Okay. And we'll see how that comes into play. But for now, the set points for my three factors, it's pretty simple. Everything wants to be maximized in order to have the best conversions. So we set the time at 50, the temperature at 90, the catalyst at the highest level of 3. Those are going to lead to the best results of the conversion at around 90%. Okay. So pretty simple evaluation, but a response surface took it there. Next, using these optimal conditions, we will evaluate the robustness against the 6 uncontrolled factors that we have. Now, here's a key point. It's important that we can control these uncontrollable factors during the robustness study itself, right? So what we're trying to do, whether it's a lab or a pilot plant or a small scale, we're trying to, I suppose you could do it on a large scale as well, but most often we're doing this on a smaller scale. But we have to be able to control those factors so that we can characterize their behavior. Okay. Now, once they go to the field, we'll understand we can't control them. But for the duration of the DOE, we have to be able to control them in order to study them. Now, in general, robustness studies are done using rather small DOEs, specifically some type of factorial design. And with small designs, we run into a couple of problems. One is this lack of this thing called power. And what's that? Well, power is the ability to discover important factors if indeed they exist, right? So you're doing a robustness study. You're trying to find out if my catalyst vendor matters. Well, if I have insufficient power, I won't be able to answer that question, right? So we have to have sufficient power to do that. We also have this thing called resolution, and oftentimes these smaller designs can be a resolution 3 design, and that would give us a problem where it'll be difficult to distinguish important effects from interaction terms, and we'll see how that plays out in a moment. So ideally, we're going to find nothing of significance. Okay, and if that's true, then we know that the noise factors do not compromise the system. However, we need to understand that the limits of that assertion, right? It's not that it has 0.00000 impact on the system. There's a certain threshold that we're going to evaluate, right? All we can really say is it does not appear to have significance below a certain threshold. So we're going to need to know how to calculate that threshold, and that's what brings us to power. So in this case, we're going to first do a really big study, okay? Not that you would ever do one of those for a robustness study, but we're going to do a full factorial, huge design so that we actually understand the impact of all these factors, okay? Then what we're going to do, once we know, quote unquote, the truth of these 6 factors, then what we're going to do is look at a couple of options for robustness studies to see if we can't glean the same information using a much more budget-friendly approach. So here's the big study. We looked at these 6 factors, and here's what we're discovering, right? So this is in studies, we use this half normal plot to identify the significance of factors. And here we can see that the vendor choice actually mattered. It was the most critical factor that we had in the system. We also found that contaminant that can sometimes be present, that mattered as well. And there's an interaction between the two. In other words, the impact of the contaminant depends on the vendor chosen. Okay, so there's an interaction term. And lastly, our temperature control for our reactor system, well, that matters as well. That matters the least. And in fact, we evaluated a plus or minus 0.5 degree change in temperature. And that actually caused less than a 2 percentage point change in the conversion itself. So at some point here, we're going to have to pick a threshold of below which we won't care. And we're eventually going to pick 2% as that threshold. So whether we detected temperature or not, it might not be that important because it actually has less than a 2 percentage point change. But let's get into that. So the kinds of designs that are often talked about out there for robustness, or also for ruggedness studies, the first one would be Taguchi designs, and Taguchi was a pioneer of this whole concept of studying for robustness. But without getting into a lengthy conversation, let me just suggest to you that while he was a pioneer, that subsequent work has developed ideas and approaches that might give a little bit better of a design than what Taguchi would offer. That said, if you're comfortable with Taguchi designs, hey, it's there for you and it's in the software. It can be used. Plackett-Burman are off-site designs for specifically ruggedness testing, where we hope and our aspiration is that we won't find anything. And the beauty of Plackett-Burman designs is you can look at a lot of factors with very, very little work. You can do 11 factors with 12 runs, for example. Okay. They are resolution 3 designs. So what does that mean? That means that main effects will be confused with 2-factor interactions. So the study might tell you that factor A matters, but it might not be factor A at all. It might be a combination of B and C or C and D or something else, okay? So that could be a problem. So the goal of a Plackett-Burman is we keep our fingers crossed and hope that we don't find anything, and then we succeeded with the ruggedness test. Regular 2-level factorial designs of resolution 3 or 4 are also considered, and I'm going to make use of a design called the minimum run resolution 4 design as contrasted with the Plackett-Burman, and you'll see some of the nuances of that as we continue. So a quick word about power again, right? So power is the ability of an experiment to reveal an effect of a given size. So the power calculation requires 2 things. It requires this choice, a business decision or experimental decision of this thing called delta Y. And that's the threshold of the factor that we feel must be discovered. Okay, and it's also, if you think about it, the value below which we are willing to disregard. So if we say that temperature doesn't matter, what we're really saying, if we pick the delta Y of 2 percentage points in conversion, what we're really saying, well, if temperature does matter, it's probably less than 2 percentage points. And if we don't discover that in the experiment, we're saying that that's okay. We also have the standard deviation or the noise in the system, and those 2 things will drive the power calculation. We did the optimization experiment in this case, and it reported a value for that standard deviation. And we're going to steal that number to use in our power calculation for this subsequent round of work. So again, an experiment with insufficient power may not reveal factor effects we care about. And for a given delta y in sigma, the power is mainly driven by the total number of runs and not so much by the number of factors. And it's kind of important that we evaluate power to ensure our DOE will meet the needs of the study. You don't want to go out there and report that, oh, temperature and vendor don't matter, when in fact we lack the power to make that assertion. Okay. A Plackett-Burman with 12 runs has sufficient power to detect effects of about 2 standard deviations. Okay, so in this example, we'll assume that our delta y is 2 percentage points in conversion and that our standard deviation is 0.76. So now we have different choices that we could pick. We have the Plackett-Burman, we have all these different candidates. I have the number of factors listed along the side. And this little table is kind of giving us some design choices that might get the job done. Note that resolution 3 are listed in red because the main effects are confused with two-factor interactions. Okay, that could become problematic if we think we find something, because we won't necessarily know what in fact it was that we found. Resolution 4 are cleaner. And what I'm going to say is, for my 6 factors, we could use the Plackett-Burman. But for the same budget of 12 runs, I could kick it up to a resolution 4, and now my main effects are not confused with two-factor interactions, right? So if it says factor A matters, it's factor A, and I'm much more confident with my results. So let's try the Plackett-Burman. Let's start there. So the questions we're going to have is, do we have enough power? And we're going to use the delta y of 2 percentage points, the standard deviation of 0.76 we got from our optimization design. So let's go into the software and try to take a peek at this one. Let me just toggle over to the file. Let's see, where is it? It's right here. Okay, so this is how we're going to build a Plackett-Burman. So first of all, in our design choices in the software, under factorial designs, we have all kinds of different things. We have minimum run characterized, regular two-level factorial, the most commonly used ones, I suppose. And underneath miscellaneous, there's this thing called Plackett-Burman. Notice also that there is the Taguchi down here as well. Okay, but here we have the Plackett-Burman. Now we need to select the number of factors that we're going to study, but look, the minimum here for Plackett-Burman is 11 factors. I only have 6. What am I going to do about that? Well, the cool thing about this design is you can put dummy factors for, I only have 6, so I have to have 1, 2, 3, 4, 5 dummy factors to get up to 11. And they're just, set at the -1 + 1 level. They're not real factors, but they're there to round out the experiment. But here, this is going to be a 12-run experiment. I have 11 factors. Technically, I'm using 6, but I could do up to 11 with 12 runs. That's called a saturated design. We'll hit next. Right, so here, just be clear what we're doing. We enter in, I've done this in advance. So we go ahead and put our factors in. We put whether they're numeric or categoric. We put their ranges, right, low and high, etc. So we've got this thing built. We hit next. This is going to give us a look at the alias structure, which is, if you're familiar with alias structures, you realize that this one's a mess. The key point is that if we're here that factor A matters, you can see that it's aliased with or confused with a bunch of two-factor interactions. Okay, so maybe A matters, maybe it's really B and C taken together. We can't tell. So we hit next. And now we got to check power. So we put the delta y of 2, right? 2 percentage points in conversion. And we're saying that if it's less than that, we're willing to disregard it, and it won't matter. The standard deviation we took from the optimization experiment. I'll click next. And the power is 98. Okay, the blue box is giving us the guideline that we want that to be at least 80. We're way beyond that. So we actually have sufficient power with the Plackett-Burman to answer the question that we have. Well, I'll go ahead and finish the design. And now I'm going to get my data. which is admittedly much easier for me than you in the real world, but here we go. So we will look at this Plackett-Burman and I have data. Now, if you're familiar with our software, you know that the next step is going to be to analyze the response of interest. In this case, I have one and it's conversion. And I'll start the analysis. And we'll make our choices of what is statistically significant based on this half normal plot. Anything that doesn't fall along that red line would be statistically significant. So at this point, we know that we've kind of flunked the robustness test because we have found things that pop off the red line. We have found things that are statistically significant. Okay, so our hopes of not finding anything have vanished. So we can click on them and we see that we have the vendor and the contaminant that matter. Okay. Well, that's good. I mean, I didn't see the interaction between the two of them, but a resolution 3 experiment can't identify the interactions. But the problem you run into here is if I right click on this, it's going to show you the potential aliases. Well, it might be factor C, or it might be a combination of A and B, or A and D, or A and E, or any of these two-factor interactions, and we can't tell the difference. So if I think about this little case, okay, so a vendor might matter, or it says it could be a combination of temperature and contaminant. Well, based on my chemical knowledge, I might be concerned about a contaminant being present in conjunction with temperature. That might be a legitimate candidate for what the problem is. I can't tell, right? All I know is that I have things that matter in the system, and right at this point, I can't tell. Okay, that's the problem with a resolution 3 experiment. So again, the ideal scenario for a Plackett-Burman robustness study, ruggedness study, would be to demonstrate no effect. But having failed that, we have a little bit of a dilemma here. So back to the slides for a moment. Let's see. Okay. So does a 12-run design have sufficient power? Yeah, actually, that surprisingly had sufficient power. That's pretty good. Do we have ailing issues? Well, yes, we do. So maybe we found what we need to know, but we're also making some big assumptions. We're making assumptions that there are no interactions between factors, okay? If we can't embrace that assumption, then here's what we're saying. Oh my goodness, we're interested in factors B and C, but maybe it never was B and C, and so we carry on with our trying to put controls on those two things, and really it was something else that we should have been concerned about. So that's the issue you have with resolution 3 experiments. Let's take another peek now. We're gonna do a resolution 4 experiment now, where main effects can be identified cleanly. So we're going to do this. We could do it with a 2-level resolution 4 experiment with 16 runs. Or we could do a minimum run resolution 4 experiment with 12. Well, the 12 is equivalent to the Plackett-Burman in size. So let's see what that design would have given us differently than the Plackett-Burman. So let's go take a peek at that one. So let me build this up. Let me get out to that example, which is where? Right here. Okay. So here we're going to build a minimum resolution for, it's called a screening design. Okay, well, that's kind of the point and purpose of this. When we look under the factorial design menu choices, it's listed as a minimum run screen, but I'm going to steal that type of design. Because it's a resolution 4, I'm going to use it for a purpose other than screening. I'm going to do a robustness study with it in 12 runs to contrast that with the Plackett-Burman. So we have our 6 factors now, right? No dummy factors, so I can select 6, and I have all the inputs just as I had before. It is now a 12-run experiment, so I will go ahead and click on that. My alias structure is a little bit confusing. That's true, but if I look at one, let's just look at D. My alias, it's only aliased with 3-factor interactions, no 2-factor interactions. 3-factor interactions in general, we're going to assume are extremely rare, and therefore we're going to take the assumption they don't exist. that is not an assumption we would ever want to take for two-factor interactions. Two-factor interactions happen all the time. So I'll click next. We're going to check for power now. So I have my 2 and my 0.76 again. And when I look, I have sufficient power, over 80%, it's over 90 actually, to find all the factors of interest. So I have sufficient power, and it's a resolution 4. I'll finish this design. There's what it's going to ask me to go do. Now I will simulate my data, and this one's going to be a 6-factor, this one. Okay, so we have data. And now we're going to analyze it just as we did before. Start the analysis. Get a little warning that this is not an orthogonal design, and all that complicated vocabulary means this. When we have one of those, we need to start at the rightmost point and work left, because the subsequent terms will move around a little bit. So we need to select them starting with the rightmost and move towards the left. Well, in this case, look, we found the same pattern, the same information that we found in, remember that first big study where we found the quote unquote the truth? We found that vendor matters, B matters, we had an interaction between the two, and temperature matters. So this one revealed everything. And if I take a look at the alias structure, I'm going to right click on the vendor. Look, it's only 3-factor interactions, and we're going to assume those are, highly improbable, shall we say. So all my main effects are only alias with 3-factor interactions. The only glitch that I have is my 2-factor interaction is aliased with other 2-factor interactions. So here's where, in the real world, we're faced with a bit of a dilemma. I might be willing to take the assumption that my interaction, the BC interaction, is comprised of 2 factors that I've already identified. And quite honestly, most of us that would probably stop right there and accept that's the most probable candidate. However, if we really wanted to know, is it BC or is it one of the other options that could exist? Well, to break an alias structure, we always need to have additional data. That's, if you have an alias problem, you need more data to break the alias structure. So what would we do? It turns out that with 50% more data, we can focus on that a little bit. Now, again, in many cases, we'll stop right here with the study and embrace the assumption that the BC interaction is comprised of 2 main effects that we've already encountered. But if we want to be really sure, because otherwise we might have to put controls on, say, A and D or something like that, well, then I'm going to want to know about that. So how would we do that? We're going to do what's called augment the design. So I'm going to click on the design up here. I'm going to go up to this little feature called augment with additional runs. And it's going to recommend a semifold. And this is going to help us with 50% more data break that alias structure. So we're going to hit OK. Well, choose a factor to fold on. Well, the fine print here says, pick the interaction, one of the letters in the interaction of interest. Well, I had a BC interaction, so let me figure out what's happening with factor B. And then we want to figure out a factor to retain. Well, what I didn't point out along the way is it seemed that atmosphere in the headspace didn't matter. I could use air or nitrogen, and I'd be equally happy. So we're going to do this fold over, and we're going to keep that factor with using only air, right? Because air is cheaper than nitrogen. So we're going to set that at its minus setting, factor E. All right. So those are the 2 things I need to do this fold over. And then I go ahead and create this thing. Now let's come back and look at it. So here's what it's done. It's created a second block of data, and now I got to go collect data for these 6 extra runs in order to sort this out. Well, let's get that data. So I'm going to simulate that, and this will be the augmented. So I go get my 6 extra runs, and there's my data now. Well, now I have to reanalyze this. Start the analysis. Let's see. what happened to me here. Okay, so there. Now I'm going to go pick the things sequentially that appear to matter. And now when I look at that BC uh, term, it's only aliased with three-factor interactions, right? So, and we're going to assume those are highly improbable. Therefore, we have sufficiently broken the alias structure. BC is no longer aliased with other two-factor interactions. So with 6 extra runs now, we're able to come back in and say, okay, here's what we need to control for this process. Factors A and B and A are the ones that need to be, controlled in order to make this a robust operation. Okay, let's go back to the slides. So we had sufficient power in this case to detect impacts of about 1.7 percentage point if you actually dig into it deeper, right? We had a threshold of 2 and we had plenty of power here. We corrected the appropriate main effects, and we found a two-factor interaction, which might be okay and maybe not. So what we did is we augmented that, and we wanted to validate that BC was the correct choice. So we carefully augmented this design, and we used air in the headspace because we decided that was not a significant contributor. And now we augmented this from 12 by adding 50% up to 18 runs. And we confirmed that our main effects and our two-factor interaction BC was correct. So now we know what we need to know with 18 runs. If we had started with the Plackett-Burman, we would have started with 12 runs. Then we would have realized, it's a resolution 3, and we found some things. We would need to double it to 24 runs in order to make it a resolution 4. Then we would need to break that BC alias structure by adding 50% more data. So in the end, with the Plackett-Burman, to get to the same endpoint, we would have run 36 runs in order to have the confidence of knowing that my three factors and that we had the correct label on the interaction term, right? So 18 versus 36. So that's quite a savings if we started with the MR4, minimum resolution 4. So conclusion, Plackett-Burman, they're effective and efficient if we can accept the assumption that interactions are highly improbable. We want to look at power to make sure that we can find what we say we're looking for, okay? We can't make the assertion that a factor has no impact. All we can say is a factor has no impact below a threshold that we set for ourselves, and that drives the power calculation. You can do up to 11 factors with a 12-run Plackett-Burman design, and as I showed you, there are choices that can take you much higher than 12 factors if you must. So the beauty of Plackett-Burman is, if you've got a lot of factors, it will become prohibitively expensive to go to the resolution 4 designs. So you might have to run a Plackett-Burman to find out something about your system. But I've shown you the risks involved with the alias structure, so be advised. My recommendation based on creating this little approach is that if you're looking at 8 or fewer noise factors for a ruggedness study, you might be better off just jumping to the minimum resolution 4 design, so that you de-alias the main effects, and if you do find something, you're much further along the journey of understanding the system. Okay, so 8, maybe 9, I don't know. But if you're beyond that, then I think the number of runs become potentially prohibitive. Maybe not. You have to decide. But the Plackett-Burman is a very efficient design. It just lacks the resolution. So let me give you a preview of other types of robustness studies. So in this webinar, we've looked only at factorial type designs, right? The Plackett-Burman, the minimum resolution 4 designs, we mentioned Taguchi. All of these are factorial type designs. But there are some tools that reside in the response surface module that can take us even further. And specifically, in the next webinar, we're going to look at the use of propagation of error. And the idea here is, when you're looking at process factors, wouldn't it be nice to find a solution that not only maximizes the performance for the responses of interest, but that solution would also be insensitive to departures from the X factor set points. In other words, it would be a robust region of operation. You built in some flexibility. Or to take it one step further, in not only set your factor set points, but let's bring into the mix the noise factors, and let's find a region in the design space that remains insensitive to both the changes in your X factor set points, but also accommodates the fluctuations you'll see, the variation introduced by your noise factors, your Z factors. Okay. So in the next webinar, what we're going to do, instead of doing all this down here in the confirmation section, we're going to bring it up a notch, and we're going to bring all of this into the optimization itself. Right? So propagation of error will bring the whole robustness effort inside the optimization to create process flexibility from the very start. So that's kind of where we're going to pick up in the next webinar that addresses robustness studies. So we covered a lot of tools in this, and more to come. And by chance, some of this may have gone, well, you might not have had the background to fully embrace and understand what I'm talking about. If you need to back up a step, we do offer some courses that might be a benefit and help to you. We have Modern DOE for Process Optimization. That's where we talk about factorial and response surface designs. We also have mixture designs. So formulation is your world. These same principles would apply to formulations as well. So you can take a look at our website for those types of trainings. I will also just quickly give you a tip that in our software, in the help section, you can go to tutorials. And let's say that I spoke about, let's just say, response surface design, and that would be a new topic for you. Well, you could come down here to response surface. It's actually a 3-part study. You could learn a little bit about response surface designs here. And so this is kind of the script, the tutorial, and there's tutorial data. So you would have the chemical conversion. That's the RSM example. So you could actually self-teach a little bit about response surface, or really any other topic. There's, like I said, there's a series of tutorials. So there's a little bit of some free training. There's also material out on YouTube that you can take a look at, as well as a whole series of webinars on our website. And once again, this webinar will be posted there within the next few business days. So that is the webinar. My first attempt to describe how to use the SADIs tools, DOE tools in general, to address the whole concept of robustness. Hopefully that was helpful to you. I don't see any questions in the question box, but if someone does have one, I will be happy to address it. If not, I thank you for your interest and attention, and perhaps if you continue to have interest and want to get a little bit deeper into it and look at the response surface tools, propagation of error, I'll see you again in, okay, I do have a couple of hands going up. Okay, I guess that was a clap. All right, well, thank you for that, and I wish you the best. If you do have questions, please send me an email at richard@stadis.com. And I thank you for your attention. And I'll give you the balance of your day back, and perhaps see you again in October. Thank you.